Alright, hello class. In this video, we're going to look at some of the other geometric things that we can do with the integral. So if we can do, say, the area beneath a curve, if we can do volumes, if we can do volumes from solids of revolution, there's a lot more we can actually do, and that's really what we're going to try and do here. These two particular topics, basically the length of a curve and the surface area, is something we can also do using integration. It's one of those situations where the formula gets really nasty, and so it's either going to be types of problems that we run into needing our advanced techniques, or they're really special cases that come up where it just all simplifies and cancels out to be super nice. Okay, so I mainly want to focus on where these formulas come from, and do a couple of examples. I don't want to get too deep into the weeds here, because these things can get really out of hand, and you'll see why once we look at the formulas for it. Anyhow, let's just get started. All right, so the first one we're going to talk about is actually the length of a curve. So if we have a curve represented by y equals f of x, and we're looking at it from x equals a to x equals b, and chart the path of it, well, it turns out that we can find the length of this curve using integration. Okay, and we do it in a similar manner that we did with areas, so if we have a function here, what we do is we split this region A to B into a bunch of smaller pieces, right? And we make sure they all have the same delta x size. They don't have to, it just makes everything easier. And then we, instead of making rectangles, I mean, that's essentially what we're doing, but instead of looking at the area of each rectangle, what we're going to do is instead take the length of all of these lines and between these points. So instead of looking at the curves, what we do is we just take a look at each one of these lines between the points, and then we shrink that down. So the total length of this curve can be approximated by the sum of these lengths of just lines, right? So we make lines and stamp them on the function. Okay, so the length of the curve which I'll call capital L, is approximately equal to the length of these lines summed together. Okay, so if I zoom in on one of these, so imagine we've zoomed in, so I have, say, the function does something like this, and we're basically just taking a secant line, essentially, and of course I can't draw, but okay, so I did the best I could, but we have a line here, and it actually makes a right triangle with between these 2 points, right? So this point up here, is the point, let's call it xk, comma f of xk, right? Because we're just taking one of these steps here. And then this one is going to be xk plus 1 f of that. Right, and let me give us a little more room here. All right, so the length of this line using either the Pythagorean theorem or the distance formula, whichever one you want to look at, okay, is going to be the square root of the difference in the x's squared, so xk plus 1 minus xk. Well, that's actually delta x, right? Because the change in the x's is the same, and I'll just call this a delta yk just to make it a little easier. So it's going to be delta x squared plus delta y squared. Okay. And then what we're going to want to do is I'm actually going to factor a delta x squared out of this. So remember, we've done this a couple times before. When we do that, we just divide everything. So when we divide it out of this, it'll be 1 plus, and then here it'll be delta y over delta x all squared. Okay, so this will simplify. If this is a particular k length, what we'll end up with is the square root of 1 plus delta y over delta x squared times delta x. Okay, so each one of these lines ends up being approximated by this right here. So the length of the curve is approximately the sum, okay, of the length of each one of these lines. All right, so it's going to be the sum of the square root of 1 plus delta y over delta x, and we look at each particular one in terms of k, whatever step we're on, times delta x. And this is the hand-wavy part. We get equals when we take the limit as n goes to infinity, which is the limit as delta x goes to 0. And when we do that, just rewriting this, when we do that, remember the sum becomes an integral, in this case from a to b. The square root, well, that stays the same. The 1 stays the same, but delta y over delta x, well, as delta x shrinks down to 0, delta y over delta x shrinks down to dy dx, which in this case, since y was f of x, that's going to be f prime. Okay, and it's really f prime of x, but yeah, f prime. It's the derivative. And delta x shrinks to dx. So we actually get the integral of, from a to b, of the square root of 1 plus, it'll be f prime of x squared dx. Okay, and that is the formula for the, excuse me, that is the formula for the length of this curve here. Okay, so, whoops. Okay, so the length of this curve we just found is the integral from a to b of the square root of 1 plus f prime squared dx. Now this formula gets nasty, okay? It's either going to break down to be something really nice, or it's going to be something horrible that requires like a trig sub or something like that, okay? So let's look at an example or two and see what we get. Alright, so let's say we want to find the length of the curve f of x equals x to the 3/2. Alright, so x to the 3/2 is going to look something like this. Let's, there we go. Okay. So it's going to look kind of like a parabola. And we're looking at it from 0 to 4. So we want to figure out what this length here is. Okay, well, we're just going to go to the formula. Right? The formula was going to be the integral from, I'm just going to write it generally, a to b square root 1 plus f prime squared then dx. Okay, so first we need to find f prime. So I like to do this in steps, right? So first I find f prime. So f is x to the 3/2, f prime is 3/2 x to the 1/2. Okay, then we square it. All right, so that's going to be 3/2 squared, so that's 9/4, times x to the 1/2 squared, which will be x. All right, so far so good, I hope. Then, well, we're going to put it in this square root thing. All right, so that's going to be the square root of 1 plus 9/4 x. All right, now from here we can just set up the integral. L is going to be the integral from 0 to 4 of the square root of 1 plus 9/4 x dx. All right, and from here we're going to do a quick u substitution. Since this is 1 plus 9/4 x to the 1/2, we can do a quick u substitution because it's basically the stuff raised to 1/2, so it'll be the stuff raised to 3/2, okay, times 2/3, and then we just divide by the derivative of the inside, and the derivative of the inside is just 9/4. All right, so, and of course we evaluate this from 0 to 4. I'm going to simplify this a bit because I have 2/3, and if I'm dividing by 9/4, that's the same thing as multiplying by 4/9. And then we will plug in the 4 and the 0. All right, so this will give us 8/27. I'll plug in the 4. Well, the 4, all that's going to do is just cancel that. So we'll have 1 plus 9 to the 3/2 minus, now we got to be careful when we plug in that 0, that just zeroes that out. So it'll be 1 plus 0 to the 3/2. Okay, so we'll get 8/27 times 10 to the 3/2 minus 1. So you can just leave this like this, if you're asked for an exact answer, I think that comes out to be about 9.1. So the length here is about 9 units. Alright, so for this example, let's find the length of the curve y equals 2 minus a half x squared on the interval 0 to 1. So a half minus, or 2 minus a half x squared, so it looks something like this, and I believe it intersects the x-axis. If we set that equal to 0, move some things around, we'd get x squared is equal to 4. So this would be negative 2 and 2. So we're really looking for this length here. Okay, so we'll go ahead and get started with our process. Our y is given, so we'll find y prime, and that's going to be negative x. Then y prime squared is going to be x squared. Okay, so when we set up our integral, we're going to have our length is the integral from 0 to 1 of the square root of 1 plus x squared. And this is going to unfortunately be a trig sub. Okay, but hopefully not that bad of a trig sub. It's going to be a tangent one. So, and there's no a. Well, I shouldn't say there's no a, but a is 1. So our substitution is going to be x is equal to tan theta, and dx is secant squared theta d theta. All right, and we'll need new limits, right? Because we have x equals 0 and x equals 1. So x equals 0, that's gives us this, that tangent theta is equal to 0. So tangent 0 and theta is 0. Okay, and x equals to 1, well, that gives us the equation 1 is equal to tan theta, and the angle that makes tangent 1 is pi over 4. Okay, so we'll set up our new integral now. Be the integral from 0 to pi over 4 square root of 1 plus tangent squared theta times secant squared theta d theta. Okay, so this becomes the integral from 0 to pi over 4 of, remember we use our Pythagorean identity, so this will be the square root of secant squared theta times secant squared theta d theta. And so what we end up with is the integral from 0 to pi over 4 of secant cubed theta d theta. Okay, and if we remember, that's that fairly nasty formula using the reduction formula. We've done it a number of times. It's been a while though. It's 1/2 secant theta tangent theta, okay, plus 1/2 natural log secant theta plus tangent theta. All right, and then we're going to evaluate this from 0 to pi over 4. So thankfully, changing the limits over here does keep us from having to use a reference triangle. Of course, some may argue that it just, well, there's maybe not much difference there. But so what we'll have is 1/2 secant pi over 4 tangent pi over 4. Okay, plus 1/2 natural log secant pi over 4 plus tangent pi over 4. Okay, so that's plugging in the pi over 4. The 0, tangent of 0 is 0, secant of 0 is 1. So the first piece will be 0 plus 1/2 natural log of secant will be 1, tangent will be 0. So this will be natural log of 1, which will also be 0. Okay, so we really only need to focus on the first part here. Okay, so the first part, secant of pi over 4, that's square root of, whoops, it's 2 over root 2, because we take root 2 over 2 and flip it. And when you, let's do it here, when you rationalize the denominator, the 2 actually cancels, so the whole thing comes out to be just root 2. Okay, and tangent of pi over, I put 2 there. That should be 4. Sorry about that. That'll just be 1. Okay, and then we'll have 1/2 natural log. The absolute value secant of pi over 4, again, is root 2, plus tangent of pi over 4, which is 1. Okay, so we can actually simplify this a bit. It'll be root 2 over 2 plus 1/2 natural log of 1 plus root 2. Okay, so there's our exact answer. Okay, so you can kind of see how easily this stuff can kind of blow up on us. All right, but you know, you take your time, you'll get there. A lot of the problems, though, don't get this bad. You'll find that MyLabs and the book, they will come up with specific examples that cancel in the exact perfect ways that you need them to be nice. Okay, it's some of them have to kind of fight with this kind of stuff, but most of them are going to, you know, not be that bad. Okay, the next thing we want to talk about is finding the surface area of a solid of revolution. So if I make a solid of revolution from a function f of x, let's say, of course we talked about how we find the volume, but you can also find the surface area of this using integration. Okay, so to do that, what we do is if we have a function, oops. So if we have the graph of a function, say f of x, and we want to find the surface area made from revolving this around the x-axis, let's say. Okay, we approach it like we did before. Okay, if this is our a and this is our b, we split our interval up into a bunch of equal pieces, okay, that are each delta x long, and we make lines just like before, but now with each line, instead of calculating the length, what we do is we revolve that line around the axis, and we get a shape kind of like this. And of course I can't draw very well, but it's what's called a frustum. Okay, it's basically if you take a cone and you hack a piece of it out. Okay, that's what this shape ends up being. It's called a frustum. Frustum. Okay, it's called a frustum. All right, so what we can do is we can calculate the area or it's really the surface area of this frustum, and put them all together, right? Because we'll get a frustum here. Okay, and we'll get another one, say, here. And just like with the volumes, just like with the length, when we put them all together, okay, we're going to get the surface area. So the surface area will be approximately equal to the sum of the area of each frustum. Okay, so let's take a look at how we would find the area of a frustum. So let's give ourselves a little zoom in. Okay, so here is a little zoom in on a basic frustum that we're talking about. The length of it is delta x, and what we have is basically a delta y here. Okay, and I'm going to say that this is, let's make this f of x sub k, and this is f of x sub k plus 1, right? So we're looking at different steps here. Okay, so the surface area of a frustum, all right, that's not one I expect people to just know, okay, but when you look it up, you find that you get this formula. It ends up being pi times big R plus little r times L. Okay, so what are those things? You notice here I've already sort of labeled things and our zoomed in frustum here. The big R is the longer radius and the little r is the shorter radius, and L is the length. Well, we've already sort of done this before, right? That L, well, one, the big radius r comes from one of these f values, and so does little r. And L, well, I mean, we already did that when we were talking about the arc length. That is just the length. That's going to be our delta x squared plus our delta y squared. And the delta y had a k in it. Okay, and so I'm just going to write this as f sub k and f sub k plus 1, just to make this a little easier. And when we simplify this, it's 1 plus delta y sub k over delta x all squared. We have a dx out here. Okay, so each one of these surface areas of the frustum, all right, the surface area is approximately equal to the sum of all these. And we let delta x go to 0. And when that happens, so when we shrink this down small enough, well, when delta x gets smaller and smaller, eventually, if I can draw it here, our two f values, fk and fk plus 1, basically become the same. They become the same f value. Okay, so what we end up with is, so as this happens, SA sub k approaches just an f of k plus f sub k. Okay, and then I'll leave this here the way it is. Okay, so, and that would end up being a 2. So the surface area equals, okay, the limit as n goes to infinity of the sum of k going from 1 to n of these surface areas, which will be the definite integral from a to b of 2 pi, so the pi comes from these two added together, f of x times the square root of 1 plus f prime of x, all squared dx. Okay, so here we go. A whole nother nasty formula that we get to play with. Okay, so part of why I'm not spending a whole lot of time here is because it's more that I want you to see the process, like where this comes from, how it works. I assume given enough time you can deal with a formula if need be. Okay, so let's look at an example of this. Okay, so for this example, let's find the surface area of the solid generated by revolving y equals 2 square root of x on the interval 1 to 3 around the x-axis. Okay, so to show what I mean there, two square root x looks something like this. And we're looking at from 1 to 3. Okay. And what we're doing is revolving this shape around the x-axis. Nothing really brand new there, except now we're only looking at the surface area. So we're not finding the volume, we're finding the surface area. Okay, so we just crank through the formula, the surface area formula. Okay, is 2 pi integral from a to b of f of x times the square root of 1 plus f prime of x squared dx. Hey, so we need to go through pretty much the same process we did before, right? So y is 2 square root of x. So we need to find the derivative of that. Y prime is 2 times 1 over 2 square root x. The 2's will cancel, so we get 1 over square root x. All right. Then we square this thing. Thankfully, because that actually does simplify that a bit. That comes out to be 1 over x. And then we're going to put that, everything we have there, in our integral. So the surface area is going to be 2 pi integral from 1 to 3 of f of x. So we just put f of x in, so that's going to be 2 root x. Then times the square root of 1 plus 1 over x, because that is the y prime squared. All right, then our dx. What I'm going to do here is bring these two square roots together. Okay, so we'll get 2 pi times the integral from 1 to 3. Actually, I'll go ahead and move that 2 out, so I have 4 pi. All right, and we'll have the square root of, now I'll bring that x on the inside, so we have this. All right, then distribute that x. And now I have 4 pi times the integral from 1 to 3 of, it'll be be x plus 1 when we distribute the x. Okay? So this is just to the 1/2 power, of course. So to integrate this, it'll just be 4 pi times, and it'll be x plus 1 to the 3/2 power all over 3/2 from 1 to 3. Okay, so it will be 8/3 pi times x plus 1 to the 3/2 from 1 to 3. Okay, so we'll plug in the 3. So we'll get 8/3 pi, and I'll put a big bracket here. So we'll get 4 to the 3/2 minus, when we plug in the 1, it'll be just 2 to the 3/2. Okay, and 2 to the 3/2 doesn't really simplify all that much. 4 to the 3/2 will. That will become 8. But honestly, you can just leave it like this if you want, as far as I'm concerned. Okay, so there we go. As we can see, whoops, definitely not what I meant to do. As we can see here, you know, these formulas really kind of get nasty. However, it's still coming from the same process that we built area off of, like area under the curve. The same process that we built volumes off of. And then the same thing we did with length, and the same thing we did now with surface area. Okay, what ends up happening is that any sort of formula you have that's based on multiplication of constants can be extended to integration if you have variables instead. Okay, so for this next example, this kind of gives a glimpse of what a lot of these kind of look like. There's some weirdness that happens here. All right, so we want to find the surface area of the solid formed by revolving this monstrosity, y equals 1/4 e to the 2x plus e to the negative 2x over the interval -2 to 2 about the x-axis. So I'm not going to really bother with what this guy looks like. I'm just going to go ahead and start with the process. I have y, so I'm going to find y prime. So y prime will be 1/4 times 2 e to the 2x, then minus 2 e to the negative 2x. And the 4 here will cancel with these 2's and leave a 2. So we get 1/2 times e to the 2x minus e to the negative 2x. All right, then we're going to square this guy. Great. So we'll get 1/4 times e to the 2x minus e to the negative 2x squared. All right, I'm actually going to FOIL this out because I want to show something that happens a lot with these problems. And I think I was saying earlier that a lot of these just come out to be perfect. So they're either going to be like a trig sub or perfect. And so here's one that's perfect. When we FOIL this out, I'm going to get e to the 4x. Okay, now e to the 2x times e to the negative 2x, that'll be e to the 2x minus 2x, so that's going to be e to the 0, which is 1. So when we FOIL this out, we're going to get e to the 4x minus 2, all right, plus e to the negative 2x, or 4x, sorry, 4x. Okay. Now the reason I did this, okay, is because we're going to be adding 1 to this thing, and I'll show you what happens with a lot of these cases. I'll have 1 plus, I'm going to distribute that 1/4. So I have 1/4 e to the 4x minus 1/2 plus e to the negative 4x, which, well, 1 minus 1/2, that becomes 1/4 e to the 4x plus 1/2 plus e to the negative 4x. Well, if this thing with the minus 2 became minus 1/2 with plus 1/2, I should be able to factor out a 1/4 and get e to the 4x plus 2 plus e to the negative 4x. Well, if this guy factored into these two things subtracted, this one should factor into these two things added. So this should be e to the 2x plus e to the negative 2x. And that's exactly what happens. 1 plus y prime all squared becomes this guy here. All right, so our surface area, right, it'll be 2 pi integral from -2 to 2. It'll be our original function, so 1/4 times e to the 2x plus e to the negative 2x. Okay, then it'll be times the square root of the 1 plus y prime all squared, which we've already, sorry, I did that wrong. I didn't put the squared there. Sorry about that. All right, and then in the square root, we're going to put the thing we simplified, which is the 1/4 times e to the 2x plus e to the negative 2x all squared dx. And the squared and the square root will cancel. Okay, so that's what makes this problem nice and manageable, is I'll get the integral from -2 to 2, 1/4 e to the 2x plus e to the negative 2x, and then this will cancel and give me a 1/2 times e to the 2x plus e to the negative 2x dx. Okay, so we'll get a 1/8. So I'll move both of these fractions out here and get pi over 4 times the integral from -2 to 2 of, it'll be these two things squared. Well, we already know what that should break out to be. Okay, should be e to the 4x plus 2 plus e to the negative 4x dx. And now we integrate. This will be 1/4 e to the 4x plus 2x. It'll be minus 1/4 e to the negative 4x. It'll be from -2 to 2. All right, and now we're just going to plug our values in. We're going to get pi over 4. Okay. And I'm going to plug in the 2, so it'll be 1/4 e to the 8, okay, plus 4 minus 1/4 e to the negative 8. So there's plugging in the 2. Now I'll subtract plugging in the negative 2. So we'll get 1/4 e to the negative 8. Okay, minus 4, then minus 1/4 e to the positive 8. Okay, so we'll get pi over 4. Then I'll have, notice I'll get, let me just write it all out. 1/4 e to the 8 plus 4 minus 1/4 e to the negative 8 minus 1/4 e to the negative 8 plus 4 and then plus 1/4 e to the positive 8. We've basically just doubled everything. Okay, so we'll get pi over 4 times 1/4 and 1/4. That'll be 2/4, which will be 1/2 e to the 8 plus 8 minus 1/2 e to the negative 8. And you could maybe distribute that 1/4 across if you really wanted to, or you can just leave it like that. All right, and I think that's probably good enough for this particular topic. So I will leave you to it, And I'll talk to you all in the next one. Cheers.